This is a lesson on the graphs of the trig functions. So we step away from the earlier exercises on algebra, special angles, things like that, and turn our attention towards the graphs. Now you will see that the graphs are very closely related to what we were covering earlier, and we do try to integrate the whole thing together. But for the time being, this will be a demonstration of the simple basic trig functions. So to begin, I'm going to start with y is equal to sine theta. And when you're graphing these, the theta, the angle, whether you're in degrees or rads, is going to be on the x-axis, the horizontal, and the y value would be the value of the sine or the cos or the tan of that particular angle. So I'm going to graph this initially in rad modes, and I will be doing some graphing in degrees, but the majority of what you get will be in radian measure. So I put my calculator in rad mode, and I enter y1 is equal to sine x. Of course, the bracket automatically opens. In fact, you do not need to close it, but I did anyways. If you graphed it immediately, you will possibly note that the graph isn't looking too good. So we have to do one other thing. We press zoom, and you have many settings in zoom, but the one I'm mostly interested in is number 7, which is zoom trig, because this zoom trig setting will adjust your window for standard trig values. Because you have to remember, particularly when you're in rad mode, well actually just as much in degrees, is that your x scale is based on the angle measurement, and it doesn't conveniently work with normal conventional values. So anytime you're graphing in trig, you do press zoom trig to start with. And the effect can be seen in the window settings. So as I said, they will set it for standard trig values. If you press window up across the top and then take a look at the numbers we've got, you will see your x minimum is negative 6.15, or should be in that ballpark. Your x max is the same number but positive. Your x scale is a quarter of that, and that becomes critical later on, but for the time being we'll just let the calculator do its work. And then your y min and y max and your y scale are more conventional numbers. You may wonder, why do we have an x min and an x max of these awkward decimals? And the reason is that that is approximately equal to 2 pi. Pi is about 3.14, so 2 times 3.14 is 6.28. And by doing this, by making the x min and x max of about 2 pi, you're basically getting a full cycle of these waves on both sides of the y-axis. So they're convenient numbers. As we go deeper into the unit in the graphing section, we do alter that quite a bit. We will change that. But this is a good starting point. So let's go back. If you did graph y is equal to sine theta, here is what the graph should look like, pretty much on your calculator. The scale might be a little bit different, and on your calculator you do not get the nice pi over 2s and the pi's and the 3 pi over 2. Your calculator cannot do those exact values, and that is a limitation because we have to do some interpretive work because of that. But this is the graph that we would get. Notice that the x and the y-intercept is at 0. And you get this classic sine wave. So many of you have run into this before in other courses. If you've taken some physics, you see this sine or the cosine curve frequently. Lots of applications for it. If we make a few observations, you'll frequently be asked to find the amplitude of a curve. Now the amplitude is not a trig term, it's just a wave term, and it refers to the height of the graph from the center to the crest. So you can see that the diagram shows that from the center of the graph all the way to the top, the crest being the top, it's 1 unit. Now that will change from graph to graph, but for just your y equals sine theta curve, the amplitude is 1. But when we start stretching these vertically, then we get different amplitudes. The next concept that we see a lot, and this can be a real troublesome one, is the period. The period refers to the horizontal distance of one cycle before the graph starts to repeat itself. So if you take a look at the curve as I've got it indicated, that one cycle would be 2 pi rads, because at that point it starts to do the same thing again, repeat itself exactly after a fixed period. And this is very important. It's important in all waves because waves typically do repeat themselves like this, and so they have a period. For the trig curves, it matters a lot. The idea that it repeats itself after 2 pi should make sense to you, though, because if you think of the unit circle, or if you just think of a rotation of 360 degrees, or 2 pi rads, everything starts to repeat itself because it's that full cycle that's distinct, and after that you're just having a series of coterminal angles. So it kind of makes sense. And therefore the period, as I did note, of sine theta is going to be 2 pi. And when we start stretching these horizontally, we play around with that period. The domain of this graph is theta is equal to a member of the set of real numbers, element of the set of real numbers. It can be anything. And it's a continuous curve. There's no gaps, no holes. Even though this is just a partial graph that I've got shown, it goes to infinity in both directions. You can take the sine of any angle. The range, though, does have a restriction, and we've seen this several times before. It's between 1 and -1. Off the graph, you can recognize that, and that makes sense from what we know about these. There's another way to write this that you run into occasionally in 30 pure, and it's the absolute value of y is less than or equal to 1. And that's another way to write it. Instead of putting the -1 as your lower limit, you can simply state that y, when you take the absolute value of it, meaning that the positive, it'll always be less than or equal to 1. And you do not have to write it like that, but you will occasionally see that. A few more observations. I've highlighted or identified 4 points in this curve, and the sine curve, because the y value represents the sine value of the angle, you can use it as you would a unit circle to get some of the values worked out, particularly the quadrantal ones, the turning points and the x-intercepts. The sine of theta is equal to 0. The sine of theta rads or theta degrees is equal to 0 because the y value is 0. If you went to the next one, the sine of pi over 2 is equal to 1. Okay? The y value is 1. We know that from the unit circle or from just a little bit of practice, but here's another way to see those same values. Keep on going, and you'll see that the sine of pi is equal to 0, another x-intercept. And then the bottom one is the sine of 3 pi over 2. So the x value is 3 pi over 2, and the sine of that is equal to -1. So that produces a y value of -1. So another convenient way to make sense of some of those values. Here's our cosine curve. So I entered this as y1 is equal to cosine of x, the same way I did sine. I kept the window settings the way they were. And you'll notice that the curve is very similar to the sine curve. In fact, it is the same shape. The difference is that the y-intercept is 1, unlike the sine curve, which had a y-intercept of 0. The amplitude, though, is still 1. If you measured from the center to the top, we would get 1. And the period is 2 pi. This one I'm measuring from crest to crest. You could actually measure the period from any equivalent spot on the wave, but crest to crest makes sense for us. And at that point, at 2 pi, it starts to repeat itself again. The domain of this curve is all real numbers. This also should make sense. You can take the cosine of any angle, and it also makes sense on the graph because there's no holes, no gaps, no anything. It just keeps on going. Not surprisingly, the range is the same as we had before, from 1 to -1. Or with absolute value notation, the optional absolute value notation, the absolute value of y is less than or equal to 1. Let's do a few observations on the graph. I'm only going to select 3 points this time, but you could keep on going. The cos of 0 is equal to 1. Well, we know that from the unit circle, that the cosine of 0 is in fact equal to 1, but we can see it on the graph. For 0 rads or 0 degrees, the cosine of that angle will give you a y value of 1. just as the cos of pi over 2 is equal to 0. Cos of 90 degrees equal to 0. Again, easy to see on our calculator, but the graph supports that. And then the cos of pi is equal to negative 1. You could keep going, 3 pi over 2 and then 2 pi. And at this point you might note that really this wave for both cosine and sine breaks into these 4 sections which represent the 4 quadrants. And more attention will be paid to that later on, but if you did recognize that, that's good. Now I'm going to take a look at both curves together. First off, the cosine one is in dark with the y-intercept of 1. The one in red is actually your sine curve. I'd like you to note that they are the same curve, the same shape exactly that came up earlier. The only thing that's different about them is their location, their orientation, or their position, I should say. The sine curve, in fact, you could think of it as being a cosine curve with a horizontal translation of pi over 2 if you were to compare the two crests. But it is important to be aware that they are the same shape exactly. And one of the things that is going to come up later in this unit is that, in fact very soon, probably by the end of this week, is that you will have to identify or decide whether a graph is a cosine or a sine curve. And you could always do one or the other, so you will have a fair bit of choice in that. That's a big part of the unit. And because of the same, every cosine curve could be expressed as a sine curve. And here's a term for you. Y equals sine theta and y equals cosine theta are called sinusoidal graphs or sinusoidal functions. So that's the general term that we use for the description of a cosine curve or a sine curve. When you can't decide what you want to call it, you just call it a sinusoidal wave or graph or function. Now here's our tan curve. Y is equal to tan theta. And you'll notice that this is a very different shape. And in fact, it is not a sinusoidal wave because of that. So only sine and cos are properly sinusoidal. With your tan graph, you get this. And you see these dotted lines that sometimes show up on your calculator. They don't show up as dotted lines as cleanly as they do here. Sometimes they can be a little bit, they can throw you off, a little misleading on that. But those dotted vertical lines represent asymptotes. And that means that our curve is approaching these values but not touching them. This should make sense because the tan of pi over 2 or the tan of 90, as we've already seen, is undefined. It does not exist. So our graph supports that you cannot take the tan of 90 degrees, that is pi over 2, or 3 pi over 2, 270 degrees, etc. So we do have an interrupted graph, a discontinuous graph, meaning that the domain will not be all real numbers. However, before we get to the domain, let's take a look at the amplitude. And the amplitude is not applicable for a tan curve. Amplitude is a wave description, and this isn't really a wave, and you can't really say what the height is because there's no crest. This thing goes up forever. So do not say amplitude is all real numbers. That would be correct for range, but the amplitude is not applicable. The period, it's possible to make a mistake on it as well. The period is just pi, because that's how long it takes for this graph to repeat itself. Not 2 pi, like the previous ones, but because each one of these strands is exactly the same shape, the period would only be one of them. So, you go from pi over 2 to 3 pi over 2, and it's pi rads, or 180 degrees. Domain, as I noted, has some interruptions in it, and it's all real numbers, which was not stated in the domain, but it is all real numbers except for wherever it's undefined or where those vertical asymptotes are. So it cannot be equal to pi over 2, and then that plus pi n, you've seen that notation before, where n is an integer, means that we have multiples of pi, which is correct, because every pi rads, or 180 degrees, we get another asymptote, that is another interruption. So that means it's all real numbers except for those, forever. And because this graph rolls on forever and ever, both directions, we have to indicate that, it keeps coming at us. You just can't list all the numbers it cannot be because there's an infinite number of them. So it takes a while to get good at that notation. However, you have seen it somewhat before when we were dealing with general solutions. The range, easy. All real numbers, up and down forever. Now, something that I didn't really draw much attention to before in the other curves is the theta intercepts. And here I do, just because it's not quite as straightforward. We do have x-intercepts starting actually at 0, and then the other one you can see in this curve is at pi rads. So I'm going to indicate it like this. I'm going to say the intercepts are where, starting at pi, and they come at us every pi rads. So I went theta is equal to pi plus pi n, where n is an integer, again meaning multiples of pi. Now I know what you're thinking. You're thinking, why didn't I start at 0? And you could have. You could have simply said that theta is equal to pi n and not had the plus pi. But it's technically correct to do this too. And that's it. Thank you for your time.